When preparing mean charts, it's important to recognize whether the scenario is a case of known variation or unknown variation in the process. The beverage company is an example of that. Let's take a look. A beverage company would like to use a mean chart to monitor how much liquid to put in each 500 milliliter bottle. Okay. They know from past experience that whenever this process is under control, bottle weight is normally distributed with a mean of. Now, this is an important reading. The process has a mean or mu of 500 milliliters when it's in control and a standard deviation of 2 milliliters. Oh, I'm definitely going to store that fact because that actually just answered the question that I posed at the beginning, right? There's two cases in drawing a mean chart. When you go into the situation and you know what the variation is in the natural process and when you don't. The fact that they told us the standard deviation when the process is in control, and I was able to write that, sigma equals 2, tells me that this is the known variation case. The variation in the process was provided. Okay, now, what are we supposed to do with it? Well, let's keep reading. Let's see, the company plans to measure samples of 25 bottles every hour. That is another important data point, lowercase n for sample size. I want to note that separately and record the mean weights of liquid beverages in the bottles. All right, well, what do we need to do? If the company uses, and the information continues, z equals 3, and as it's standard for establishing a mean chart, where will the upper and lower control limits of that chart be? That is, in the case of known variation, the chart will essentially be created by taking the mean, right, mu, adding and subtracting z times the standard deviation in the process divided by the square root of the sample size. That's the formula that we need to set those limits. They're asking where's the upper and lower control limit, right? Oh, the z, right, they gave us. Oh, the other stuff we found in the paragraph. This business here, sigma divided by the square root of the sample size, that's the standard deviation in the sampling process, or the sample means. Okay, well, we just need to find in the limits, just fill in that formula. Fill in that formula. For instance, the upper control limit, UCL, would be mu, or 500 in our case, plus, choose the plus this time, 3 times, all right, sigma is 2, divided by the square root of 25, which I get results in 501.2 milliliters. Okay, that's the upper control limit. The lower control limit, we're using the same expression again in essence, 500, except now we subtract out that same z equals 3 times 2 divided by the square root of 25. So in this case, I get a lower control limit of 498.8 milliliters. And that's it. That is right there all we need to do to answer that question. So in the future, when they're pulling these samples of 25 bottles, they just need some graph paper where they plot the 501.2 milliliters as a border or a boundary and the 498.8 milliliters as a boundary, and whatever the average sample weight is, they plot it. Hopefully it's in between, because if it falls outside, that's a signal for assignable variation. Anyway, they didn't ask about that, they just asked for the limits. There they are. Now, what's this other question? For legal reasons, the company cannot tolerate more than 501 or less than 490 milliliters in each bottle. That right there is a design. I'm going to write spec or specification. They're saying it's got to be this way. What is the process capability index value for this bottling process? What does it indicate about the process? Oh, all right, so we need the formula for the process capability index. noted as C for capability, sub P for process. What is it? Well, it's a ratio. It's actually pretty simple. It's a ratio. In the numerator is the design specification width. And it's a ratio, so what's in the denominator? Essentially 6 times whatever we were told the standard deviation was. Oh, because the process capability index, it's a score, right? A single number, but how do you calculate it? It's a ratio of the width that the design will tolerate to the natural width of the process, and it's agreed that the natural width of variation in the process is 6 sigma, or 6 times the standard deviation. So, first off, they asked, what is the process capability index for this particular situation? We need to fill that in. It's pretty simple, because we just say, okay, the width. They said 501 down to 499. That is the width right there. And then 6 times, well, they said 2 milliliters. So it's 6 times 2, or 12 in the denominator. So I get 0.1667 in essence. That is the process capability index number for this particular process. They also ask, and this is important, what does it indicate? What do you do with a process capability index number? It's a signal. If this number, once you calculate it, is 1, at least 1 or greater, ideally greater than 1, it is indicating that the process can support production. It can support the design specifications, right? Its variation, its natural variation is not so extreme so as to violate the design specifications. If it's less than 1, it's signaling that this particular process is not a good match for this particular design. This particular process is not capable. That's why it's called the capability index. It is not capable of doing a good job in production. Oh, so this is definitely less than 1. Well, we would want to say that. What does it indicate? This indicates, meaning the 0.1667, that the process is not capable of supporting, I'm just going to write production, but by production, I mean production of these design specifications here. So, we'd better find a different process.